So today we're going to look at Le Chatelier's principle. Le Chatelier's principle and dissolved carbon dioxide. Now remember, Le Chatelier's principle is if a stress is applied to a system at dynamic equilibrium, then the system will move in a way to reduce the stress. So basically, if a system is pushed one way, it will react against that to counteract it, and it will come to a new equilibrium. And let's have a look at how that would apply to dissolved carbon dioxide. So here we have carbon dioxide dissolving in water, and as one is dissolved, another one comes out of solution at certain temperatures and pressures. And this means it's an equilibrium reaction. So because it's an equilibrium reaction, Le Chatelier's principle applies. So you see that as one leaves, another enters. And it's a dynamic equilibrium. So the concentration, so things are reacting constantly, but the concentrations of both stays the same. So here is the summary of this reaction. Okay, so it's like 3 steps to it. This is the summary of it. So carbon dioxide gas plus water, liquid, gives you an aqueous carbonic acid. Okay, so that's your carbonic acid. So carbon dioxide as a gas dissolves in an equilibrium reaction to carbon dioxide aqueous. Then the carbon dioxide aqueous reacts with water in an equilibrium reaction to give you carbonic acid. Okay? Then the carbonic acid reacts in an equilibrium reaction, so it dissociates as a weak acid in an equilibrium reaction to give you hydrogen ion plus hydrogen carbonate ions. Alright, so there are several equilibrium reactions which all add up to this summary equilibrium reaction here, and we'll have a look at how that works out for us. So if we change the temperature, the first thing we need to know is that this is an exothermic reaction, which means delta H is negative. So it's an exothermic reaction. So if we increase the temperature, that actually means it will drive it towards the reverse reaction. So if we increase the temperature, it'll drive it towards the reverse reaction because it will want to counteract that added heat. This is a problem because as the oceans warm up because of more carbon dioxide in the atmosphere, they will then release more carbon dioxide into the atmosphere, which will cause them to warm up further, and then they will release more, and so forth, and it becomes a bit of a scary feedback loop. As the forward reaction is exothermic, if we decrease the temperature, however, it will move in the forward direction. So when we change concentration, essentially we are either adding reactants or taking them away. So if we increase the amount of carbon dioxide in the solution, so if we increase the concentration, that will then, the reaction will go, there's too much carbon dioxide, it's time to use it up, and it'll drive the reaction towards the forward direction. If we take any carbonic acid out, it'll still see it as an increase in concentration of reactants and drive it towards the forward reaction. But if we take out carbon dioxide, it will cause the reaction to drive towards the reverse side, so the reverse reaction. Or if we add carbonic acid, that will increase that concentration and it'll try and counteract it, and we will drive our reaction once again to the reverse direction. If we change the pH, in this case, pH is kind of a change in, it's a change in concentration of carbonic acid. So if we decrease the pH, essentially we are adding hydronium ions, or adding hydrogen ions, which is just down here. This increases the concentration of the hydrogen ions, which drives this reaction to the reverse side. This increases the concentration of your carbonic acid, which will drive this reaction to the reverse side. This will increase your concentration of aqueous carbon dioxide, which will drive this reaction to the reverse side. So you see, if we change the pH, if we add hydrogen ions, eventually it gets to a point where that drives off the carbon dioxide gas. If we increase the pH, that means we add hydroxide ions, this will take the hydrogen ions out of the solution. So it will actually decrease the concentration of hydrogen ions, which will drive this reaction to the forward way. This will then decrease the amount of carbonic acid, which will drive the reaction to produce more. This will then reduce the amount of aqueous carbon dioxide, and that will finally cause the oceans to absorb more carbon dioxide. The pressure and volume changes is the final one we're going to look at. If we change the pressure, if we increase the pressure, as we know, it'll drive towards the side with the least gas molecules. So, if we increase the pressure, it will drive it in the forward reaction to reduce the amount of gas molecules. If we decrease the pressure, however, it will want to increase the pressure to reduce that change, and that will drive it towards the reverse reaction. So if we decrease the pressure, like when you open a can of soft drink, that will cause it to drive towards the carbon dioxide as a gas, which is why when you open a can of soft drink, you hear that fizzing sound. That's all the carbon dioxide leaving. Alright, I hope that made sense. If you have any questions, ask them in the comments below. We'll get back to you as quick as we can. Thanks for watching. See you next time. Bye now.